I am Roland Kuhn. I am leading the akka project at Typesafe. So we have a team of 5 people, me included, working on akka. And yeah, you probably know most of that already, but it's always good to give the context. And this time I am going to present something that I have not yet spoken about at a conference. So it's always a bit, I'm always a bit nervous about new presentations. So let's see how this one goes. There seems to be at least enough interest. This was also very much predictable, I think, because the one most common complaint people had about akka was not that it's slow because it's fast enough or that distribution doesn't work because that's what it does. No, the complaint was that actors are based on functions from any to unit. Telling a message is any to unit, receiving a message is any to unit, and there is not much restrictions in that. You can write any code whatsoever, it will compile, and you don't really know what happens until you run it. This gives you a lot of freedom, but still people asked for some help. So this will be a rather hands-on talk, so let's dive right into some code to show what I mean. You see here a very, very simple actor. We have 2 messages for getting something and the reply is that we got something, and this actor just gives us back something. It's a trivial example. Just keep in mind the protocol. There's a get and a got, and when you send a get, you get a got. Okay. Now, let's make a very simple client that uses this, this information that it can get from the other actor to provide someone else some more information. So this one can extract references from the map that the other actor provides. So it has a getref command, and there's a getref reply. So you can look up a name in this map, a string, and then you get back the actor ref. This is realized using here some worker actor that will wait for the reception of the actual map, and when it comes back, oh, I hope that the green is a bit funky. So when that's got map, and then we send back to the original client what we find in the map for the name. So this is a really trivial example, because the point is, when we refactor this, so let's say the actor that implements the store, the key value store, so to speak, we want to somehow be able to know which reply it is that we just got, to which request it belonged, so we add an ID field. Could happen. So we add it. There's a case class get now and a matching ID field in the case class got. Because we did this change on purpose, it is very likely that we will make the necessary adjustments in the server here. And then someone might just hit compile and see what else breaks, because that's how we develop Scala programs. We let the compiler guide us. The compiler will tell us that this match down here will need to be adapted, because it had 1 parameter and now it needs 2, so there will be a compiler error, we'll fix it. This was supposed to be a green box, by the way, but green is a bit funky on this projector. What the compiler will not tell you anything about is the case up there, where we tell get to the server. It's a case class, it has a companion object, and the compiler will happily send this companion object to the server actor, which will then just ignore it because it doesn't know what to do with it. And yeah, there is no protection against that unless you actually run the code, which means writing tests. Of course, you need to write tests in any case, but it's a longer round trip time to run the full test suite and then see, oh, this breaks, then you go figuring it out. Wouldn't it be much nicer if the compiler could just tell you? There's another thing that has been bugging me at least, and I guess many of you as well, and that is we could also have implemented this not with a per request actor, which I've shown. You can also just use the ask pattern. And when you ask the server for this get with the parameter 42 now, we get back a future of any. because we don't know the types currently. Then we need to have this operation map 2, where we stipulate that we will have a got message in our hands, and then we can use it. But there is no checking here whatsoever. It's just a cast. We just assert this will be this type of message, but the compiler cannot help us figuring out whether that is actually correct or not. So we want to somehow fix this. This is a very old story. It begins shortly after I joined Typesafe. In akka 1.2, who remembers still akka 1.x? So who has used it? Those are the minority now, because akka 2 is so much better anyway. But so in the old times, we had the exclamation mark for sending a message, fire and forget. We had the double exclamation mark for get request response, which would synchronously await the response. And we had the triple exclamation mark for returning a future. And I mention this because there was actually a difference in how you had to reply in your actor based on whether it was one exclamation mark or multiple that were used when sending the message. And I tried to introduce a unified abstraction that would make this work no matter whether it was a future that is being fulfilled or an actor message that's sent back, and I called it a channel. A channel is something that can consume messages, hence it's covariant in its type parameter t, and it was supposed to unify both actor refs and futures in a certain sense. Now, if you see this comment, I said real static type is impossible without runtime costly manifests. Which just proves that I didn't really know what I was doing back in the day. Then, well, as I learned more and got more educated and grew in the akka ecosystem and also in the Scala ecosystem, I was very excited when Scala 2.10 came out because it had macros. And macros made everyone just go very, very fancy with their wishes of what they want to express. So one of them was me doing typed channels. Typed channels was a revival of the idea that we can have actor refs that have fully statically checked type information, but they should just work like akka actors always do. So that led to some difficulties. What I wrote was a slightly changed DSL with these funny arrows because I wanted it to make clear that these are typed interactions, and all these would use macros in the background to do the type checking because the types that you needed to write down were quite complicated. They were actually type maps, and the feature that caused this was the automatic sender capture. When you send a message from one actor to the other, we grab the self-reference from the implicit scope and put it in an envelope together with the message, and then at the recipient you can say who's the sender and send a message back. The problem is that this method that you will have to have in the actor, which is called sender, needs to return a certain type. And it doesn't know what the sender of the message had, what the type was, because that's really dynamic. Unless we can restrict it, so I made these H lists, and yeah, it was a bit complicated to write down and not very intuitive, I thought. But the other problem was, I mean, this is just a very tiny excerpt of the kind of code that you have to write to make this work. And then there's also no chance to make this work on Java, and well, Akka has always had this Java story as well. So to summarize, first, we didn't really know what we were doing. Then we tried to go too far and just tried to model everything, and it got really complicated. One of the things that really showed me that this is not going to work is when people told me, yes, but macros will not be expanded in an IDE. So you're back to programming in VI, I guess. So that didn't really work. Then I realized, so we removed type channels after the experimental phase because it hadn't worked out. And I realized that the approaches were not bold enough. Because there are simply features that make it really hard to express what current akka actors do with static type information. Now let's approach slowly the solution. First, so we do the magic thing here. We say what we want first. So what we want is a parameterized actor-ref. We want an actor-ref that can tell us what kind of message it accepts. How would that look like? So we take the example, the get message with the ID. Now we need to get around this sender restriction. And there is a very simple and effective way to do so. In the message, we can state that the reply to this message will be of type got. So we need to have an actor-ref that accepts this type so that we can send the reply. And there is a very obvious place where we can put it, namely in the command itself. So this means in the get, we have a reply to actor-ref, and the got then will be sent there. We will not use the implicitly captured sender, because that would have to have type any. Then we do the same change for the client code. Again, the reply to, in this case, will be a get ref reply. And then when let's say we have an actor-ref that accepts these get requests, no matter where we got it from. We can write the client's behavior as a partial function from any to unit, as we know, matching, saying if this is a get ref of some name, that's name in there, then we ask the server for the map using get, and this will be statically checked. The compiler will tell us if we send the get companion object, because that will not have the right type. But what you also see here, if you're used to Scala and curried functions and things like that, well, I wrote server.get42 and I left off the second argument list. So what I pass to the question mark, to the ask operator, is not actually the message. It's a function where you can embed a reply to actor-ref to get the message. And this means that the question mark operator now knows which type it is that will come back, because it knows what kind of actor-ref it has put into the function. That's what type inference can do for us, but only if it's a curried argument list, by the way. Martin said he would fix that in Dotty to make it work with an underscore as well. So anyway, we ask the server and we get back a future which has the correct type. So we map got and it has the right type. And then we have the reply to address where we send back the get ref reply with the lookup in the map. So this is one thing. This is what we want in short. We have actor refs that the compiler can statically reject the wrong messages for. And we have futures of the right type. So the guiding principle here is, well, we build everything around this abstraction of a contravariant actor ref. A restriction that I placed on this is we do not want to use macros for this because we want it to work in Java as well, which means that we also cannot use fancy things like higher kinded types and anything that requires complex type signatures would just break down in Java code itself because there's no type inference. So keep it simple was really the recipe here. And then starting from these, those are real restrictions. But they, I thought, will yield something that's useful. So let's just remove everything that does not work with this approach. So, in particular, the implicit sender will be completely useless. So that's clear from the beginning. So the possible plan might be that we just add a type parameter to actor-ref. How do we get these actor refs? Well, we get them from props, which we get from actors. So all these would need to have a type parameter. An actor would declare what kind of type it can process on the input side, and that would be put onto the props as well. And then we call actor off. We get an actor ref of that type back. That would be cool. We remove sender, as I said. Then there is something more we can do. We can say that the receive type is no longer any to unit, it's type T to unit, because the actor has declared what it is willing to ingest. And that makes it possible to write functions that give you all the nice exhaustiveness checking of your case classes. If you use a sealed trait for your commands, for example, it can tell you, you forgot to handle this case. That would be really useful. Then, of course, context.become is a bit worrisome, Because context.become, you can change your behavior. And if you could change it arbitrarily, you could break the contract. You said, I handle server commands, and now I switch behavior to being a client. That wouldn't work. Because then all the static guarantees would be broken, all bets would be off again. So context become would need to be restricted to keep the same type. You can't change it. The reason for that is quite clear, because it's not, otherwise it would not be a static property of the actor. So if we do this, type safety is achieved and everyone's happy, right? Are you happy now? Well, I wasn't quite. Because there were still some other things that didn't quite fit. For example, we have these life cycle hooks in the actor. These life cycle hooks are a bit besides the nice things, because when you use context become, that's especially troublesome. You have context become, you use a closure for managing your state without using variables, because you find that maybe, like I do, a bit more manageable to keep mutability in check. But then you cannot use the current state that you're actually in your post-stop hook, for example. You cannot react to the state that you have accumulated unless you use variables. There were a few other things. People used to have, or still have, big trouble closing of a sender. That's gone. But still there is the context, the actor context, where you can call actor off on and watch and so on. And if you accidentally send that to another actor by putting it in a closure, then really bad things will happen. So I thought, can't we just go a bit further? There was this smart guy. In 1973, he wrote this paper, which basically we have now implemented. And an actor can do three things, he said. It can send a finite number of messages to actors that it knows. It can create a finite number of actors, and it can determine the behavior to be applied to the next message. Those are the three basic principles of the actor model. We have implemented that, but in a little bit curious fashion. We have not really taken this last sentence, part of the sentence, very seriously. And I thought, if we were just to do that, then many things will fall into place. And you'll see that in the following. So now I can also explain what this funny A with the circle above thing word is all about. Gålbma is the Sami word for three. Sami is the language spoken in Lapland, in northern Sweden, Finland, and so on, by the native tribes there. It's pretty close to Finnish, so it means three. So this is a code name for what we thought to be going towards akka-3. So if we ever were to do a third epoch, that would probably be it. And this means, so if I'm breaking all code out there, because ActorRef now needs brackets after it, I might as well fix a few other things. That's, yeah. Let's just clean things up a bit. So that's Project Gålbma. And the main theme here is that we distill an actor to what it really is about. It's about behavior. An actor is just a cell in which you have some behavior, and you get messages passed in. The behavior processes the message, determines the next behavior, and then it processes the next message. That's how it was meant to be. That also means that everything does need to be a message, for real. It wasn't really. You had these life cycle hooks, and they are not really exposed as messages, and that was problematic. And the other thing is this actor context being closed over and so on. So let's see whether we can fix that. And well, let's see whether we can do a few more nice things going in the direction of making actor behavior actually composable. People say actors don't compose, and I suppose what they mean is that the code inside of them is, is this mutable state tangled mess. You can write it in a more intelligent fashion, but still, with the current tools that we give, what you write inside an actor is difficult to compose. You don't have pieces that you can readily reuse. You always need to think because you're modifying state. between actors, there was always composition, but not in the functional way, but in the sense of protocols. I'll talk about that a bit later. So, and I'm currently exploring on the last line, the completely pure formulation of actors, but that's a bit far out. So let's first see what this means to distill an actor to its essence. So I said we have these lifecycle hooks, and we have they are most of the methods on the actor trait. And when I removed them, basically just the receive method was left over, and I just said, oh, okay, let's remove the actor trait. It doesn't really serve a purpose anymore, so it's just behavior now. What we have here is the complete class. You have seen the protocol get and got. I inserted a put here as an example to make it a bit more interesting, and made a sealed trait for all the commands that the actor speaks. But this is all not put in a class, it's put in an object, because these are static definitions of message types. Why would they need to be relative to a class instance? And then we need an entry point for this actor. We need it to start with a certain behavior. And this is a behavior that accepts commands. So vol initial is behavior of command. And now we need to write a behavior. You'll see a bit more about the definition of total here. What you will probably notice is that this looks a bit like a receive block that has some funky annotation in front. So this is a total function that's in there. It's not a partial one anymore. And it accepts commands. That's what it says. And then we go on with the normal case statements matching the things that we get. So when we get the get command, we send to the reply to the got with the map, and we stay in the same state. No changes. But when we receive a put, we actually change to a new state. This is the with map. So we just update the map that we had in there with this new key value binding, and we create a new behavior. This is what it means to return the next behavior, to determine the next behavior before you process the next message. And this, as it turns out, solves many of the problems. So how does this look like? This is the complete and actual definition of the total case class that extends behavior. Behavior has two methods that need to be implemented. And so the def message there is the interesting one for now. So this accepts messages of type T. And it also accepts the actor context for this type T, so that the actor code can actually do things like spawn other actors or watch other actors, react to life cycle. Reacting to life cycle things is done in the management. So that's the other thing I'll talk about next. Sorry. So the important part here is that the context is passed in. And you know, when it's passed in, it's always a value. If you close over it, in any closure you write, you close over it by value and not by reference anymore. So this removes several points where things go wrong. But the next thing is, well, everything is a message now for real. So we have, if you have a full command, that's not only interested in the message type T that you get in, but you can also react to these other things. So we have messages. There's a wrapper for that. That's the top case. That will be type T, a command in this case. And then you have 7 different signals that the actors can react to. It's the 4 lifecycle hooks that are now properly expressed as messages. And you can handle them in the context of the current behavior. You have supervision. The failed message replaces the val supervisor strategy that we had. And receive timeout on terminated also needs to be fit in. Those were normal messages before, but they are not subtypes of T, of the T that you declare. We would need .T and union types to make that work, but, well, we don't have .T. So this is why those are signals for now. The actor context that gets passed in here remains the same thing. It has the same function of allowing you to access the system interface, the actor system, perform operations like spawn, stop, watch, unwatch. Then schedule is used very frequently, so it might make sense to offer it directly on the context instead of having to say context.system.scheduler.schedule. So yeah, a few cleanup actions here and there are mixed into this. Then there is also actor off, so spawn is the new actor off. A new name is probably appropriate since otherwise it's too much confused. Not only by the compiler, because overloading is always a bit difficult, but also by humans. So actor-off gives these new typed actors the ability to create child actors that are old untyped actors. So this whole thing is meant to interoperate cleanly and smoothly with current untyped akka. Then there is one thing in there, spawn adapter, that we'll talk about next. Because you probably asked yourself, if I have only one type T that I can specify, that's very, very limiting. How do I speak a foreign language? So I'm this actor, and there's that other actor over there, and that actor has its own language, its own case classes. They are not members of my command type hierarchy. How do I receive the replies even? Well, that was one of the things that type channels tried to do, and that's why it had these H lists and was very complicated. Yeah, I think this can also work. So let's say we have getRef and getRefReply, and we declare a third message. That's a got wrapper, where we just model the semantics of this other actor's language, but put it in our own hierarchy. Then the important call here is context spawn adapter. Spawn adapter creates a child actor. Logically, it could be optimized later to be very efficient, but still, it's conceptually its own thing with its own actor ref, and it is created from a function. The input type determines what kind of message this adapter ref accepts, and the output type needs to fit into the current context's type. And this means that the reply goes via this adapter into the current actor. So we can basically subsume a foreign protocol into our own language for speaking it. The other thing that's visible here is that behaviors, as I said, should be composable. There's one example here. There's a decorator. Context-aware is a behavior implementation that upon receiving the first message, the pre-start, will extract the context, run the function that you give it, and then defer for all further messages to the behavior that you construct and return. This allows us here to create this adapter and create the behavior parameterized with this adapter's actor ref. So this is again a total behavior which keeps track of a counter, next ID, and remembers what kind of replies it must send back to which clients. And so this is just a normal way of keeping track of state in a way that doesn't use any variables. So this is shown here. So shall we take a look how this actually is done? I mean, this might seem like, yeah, we've done some fancy things, but how does that relate? Currently, this is a completely independent add-on library that sits on top of akka-actor. There was only one tiny modification necessary in akka-actor to make the things work, and you have not yet seen the effect of that. You'll see it later. It's, as I said, layered completely on top, and it's quite small. It's 2,000 lines of implementation and tests. And the goal has been to be fully interoperable. So you can send messages between typed and untyped actors. You can have parent-child relationships either way between typed and untyped actors. It all works. Now, this is the single most important class, or interface, if you will. Looks very simple. It has just a single type parameter. So I have high hopes that this can be efficiently implemented in Java, also source code-wise. It will not be overly complex. It doesn't have any of these H lists on it and so on. And it captures the essence. We can get a message or a signal in to the actor, and that results in the new behavior. And that allows us to write some generic code that we can do. So first of all, we can have different ways of implementing it. You've seen total and full, I think. There's also partial and static. Static corresponds to the old way, so the old receive type. That doesn't return the next behavior, just like the old receive didn't. It's just a side effecting T to unit now. Then you can have decorators, like you have seen context aware. I like the name self-aware, although it might be a bit too much, saying too much. Then synchronous self is something that gives you an internal actor ref where you can send back into the wrapper, and it will be synchronously executed before taking the next message out of the mailbox, which is really useful if you want to have two sides of an AND or OR combinator talking with each other. So yeah, there's a whole wealth of things that I can't really deeply go into now. So I said there was one thing that was changed in akka-actor, and that was to allow actor system to be fixed. Actor system has this one method that I'm still sorry for, and that's called actor off. When you call system actor off, what happens is that an actor will be created, but it will not be voluntarily created by its parent as it should be. No, it's pushed in from the side, like cuckoos do it, right? I think that these birds. So it doesn't really have consent from the guardian actor when you call system actor off. And that is not only morally problematic, it also led to lots of very complicated code to write. And it's interesting that these two mirror each other so well. That was one thing that always bugged me. And so I thought, let's just do away with that. But if we don't have the ability to create top-level actors anymore, how do we start? I mean, how do we get going? There's just a very simple answer to that. When you create an actor system, you just give one props to it, and it will create the guardian from these props. And that's the one change that was necessary. So here, a guardian is defined, again using context-aware to create the server and the client, and then a static behavior, which unfortunately is barely readable, but any message that you get into this guardian will be forwarded to the client, so that you can basically send a message to the guardian and speak with the client. Then the system is created with a name, demo in this case, and the props for the guardian. And then we can just communicate with the system, because the system acts as if it is an actor ref. And the actor ref that it is that of the guardian. So you can speak with the guardian actor. And if you need to ask it to create actors for you, of course you can do that. You can create top-level actors, but that needs to be done voluntarily by the guardian now, and you get a future back. And that makes everything so much more consistent internally and work much nicer. So yeah, we asked the system here to get ref and then map and print line, and in the end terminate the system. So, does this look good so far? Who totally hates it? Okay, that's whew. So testing. There are interesting consequences in applying this last fragment of the sentence from Carl Hewitt, that executing a behavior returns the next, and then we also pass in the context to make it more difficult to make a certain class of mistakes. This has interesting consequences, because we have now described something, the behavior, that can exist in total isolation. You've seen there was no need to create it inside a certain context. You couldn't create an actor. If you said new something extends actor somewhere outside of props, you would get an exception, because the execution and the logic is just baked together. Now it's separated. We can just create behavior freely. We can also execute it in any way we want. So in tests, we could have an actor context. You still need to pass a context in to be able to run it, but the context that you could write Doesn't need to be the asynchronously executing dispatcher-based one. It could be completely synchronous. And it might, I mean, the context is the window to the world. If you control that, you can mock out any interaction the actor has with the outside world quite easily and inspect the effects that happen. So just to give you a taste of how that might look like, I wrote something called a receptionist. It's not really that important what it does. You can register, it's a key value store for service keys to actor refs. So you can say all that speak this certain protocol are registered here, and you can get a list of them back. So there is this effectful actor context that is there for synchronous execution and gathering all the effects. There is inbox.sync, which is which hosts an actor ref that is backed by a simple queue. So whenever someone puts something in, you get to pull it out afterwards for inspection. And then, that's supposed to be context.run with the message register, service key, and so on. So context.run just puts a message into the current behavior in this context, evaluates it, records the effects, and takes note of the next behavior. So when we say context.run the next time, it will go into the next behavior. But in between, we can make assertions like get all effects, and we want to, in this case, be sure that the registry properly watches the actors that get registered, and, well, nothing else should happen. So the get all effects should be effect watched, and nothing more. And the reply that we should have gotten is that this service was actually registered, and we get it in these synchronous inboxes. So then in the next step, we try the command that will find services, and for that we need an inbox that can consume these listings. So same thing again, and there should be no effects this time because it's just a query, and we should get the correct listing back. And this runs fully synchronously in microseconds. You don't need to asynchronously dispatch, have timeouts, and then on Jenkins the timeouts are never long enough because you run it on EC2 and it gets scheduled out and tests fail and are non-deterministic. No, this is fully deterministic actor testing. This is, I think, a really, really good step forward without any funky stuff like calling thread dispatcher that always breaks things. So this I think is a huge effect that it will have on the way you approach writing actors. And it's not about the typedness. This is about just decoupling the execution from the logic. So what can we do with this? We can get a bit fancy. We could, for example, think, oh, I have this class. Let's call it my class, and it has a method, my method, that returns something. It has some other method that doesn't return anything, and it has a protected method that does something else. So how do we translate this into an actor? Because we have added types, and types usually mean we want to express objects that have these types and members, and wouldn't it be nice? Of course it is. It's just a more or less mechanical transformation. It's now an object, my class, and it has case classes for all the methods that you had. I've used uppercase here just because that's convention. So you go through and uppercase everything, you change def to case class. We had these protection levels. We had public, protected, private maybe. It turns out these can be modeled. So there's an all command, which is what contains all the members, but that's not necessarily what you need to expose to the outside world. So you say, I handle all commands, but I only expose a certain subset. So the command extends all command, and the previously protected method helper extends all command. So it's not accessible when you just have an actor of command. Then you declare the behavior to be behavior of command, which is the full behavior here. It's a behavior of all command narrowed down. So you choose to expose less capabilities to the outside world. And you can actually, it's pretty obvious, you can have different traits that encode different protection levels, or you have lots more flexibility than just public, private, and protected here. Also, This was just a mechanical transformation, basically. The reply to was whenever you return something, but I'm pretty sure all method signatures that you can write down can just be translated like that, and it would just work. So I do think this is a full model where you can expose the object types that we have in Scala just in an actor fashion. Now, let's just compare how it looks like using these classes. So first of all, normally we have a value myClass of type myClass. We have a value myActor that's now an actor f of command, or myClass.command. That's a difference. So you can't really access the actor itself. That's still actor encapsulation. But then the differences are not that big. You had myClass dot for selecting methods. We have turned methods into messages. So we replaced the dot by an exclamation mark. Done. That's completely enough if there is no return value. If there is a return value, well, we need to get it somewhere. So if it's just a single return value, which is what methods can express, then we just use ask. So we turn the dot into a question mark. Done. So you can express all the things that you normally do to compose your object-oriented code as actors with proper type checking, with the same level of type checking, with even more flexibility in the type checking. So this is quite exciting already, but they are actors. They can do even more. Let's see. We have here the definition of some messages that might be exchanged between some actor and some authentication service that can give you a session. You say get session and you get this get session result back. Get session result could be an active session or a new session. Active session means that you get an actor ref for the session commands where you can interact with the active session. Then you're finished. But new session just gives you an actor ref where you can send your authentication credentials. So authenticate has username and password, and then a reply to that takes an authenticate result. An authenticate result could again be an active session or a failed session, which, I mean, password didn't match or whatever. This is nice, but this is not the nicest way to look at it. A nicer way, I think, is this. So you can just draw these types, and you just note the relation of contains an actor ref of. Get session contains an actor ref of active session and or new session, and so on. So you can make these arrows. And this is a depiction of the protocol that is being spoken. And you can clearly see that there are two paths or three paths of walking through the different states of the protocol here. Actors can express more than just request response. Objects and method calls have only request response. We have learned to live with this limitation, but actors don't have it. Actors can send you multiple things back, or they can come back via different routes and so on. They can forward messages. They have a lot more freedom, and we have a lot richer vocabulary for speaking about protocols that model an interaction between two entities. So what can we express? I think we can express everything that a normal module system with these members, methods, and so on can express with actors. But we can express more. We can pass object references for channels, for messaging, and so on. They can have rich interactions, patterns beyond request response. We can do dynamic things like delaying messages or not routing messages or batching messages or doing things with time in the system that you can't do with method calls. A method call just happens always now. There's no freedom here. But with actors, you can do lots of things, lots of transformations, throttling the access, the access rate to a certain service, for example. But I mean, it doesn't do everything, right? Nothing does everything. There are things we cannot express. Well, the first limitation is, well, quite obvious. We can only express at compile time the statically known things. We can only express what we can actually know at compile time. That's obvious. The second one is that could actually be fixed by a richer type system. We cannot do session invalidation. So when you walk along this graph in a protocol, We cannot force the compiler to make invalid the actor refs that you had previously. You will always be able to hold on to them and use them later, even though that doesn't make any sense in the protocol. That is a limitation that might be interesting to fix. I don't know. So that brings me to the summary. This is currently released as part of 2.4 M1. It's not experimental in the way we normally label experimental modules. Experimental means it's basically done, but we reserve the right to change APIs for one more version before we lock it in. No, akka-typed is still research. Think of it as experimental squared or something. It's there, it has docs, but currently it's just bare actors, as you've seen. No persistence, stashing, and so on. No Java API yet. You possibly don't care about that. I do. So the next steps will be we should add a proper Java API. Then these receptionists will eventually replace actor selection. And we might look into using akka distributed data for managing which actor lives on a cluster using conflict-free replicated data types. Then also, there's a lot of work to be done in making use of this power of types in the APIs that we already provide and that are currently untyped, of course. There is no FSM support yet. As I hinted, we could do something a bit more interesting with expressing effects without actually evaluating them, putting everything an actor can do in a sort of actor action monad, which would be a completely pure way of formulating actors, which would enhance testability even more and enhance compositionality of the internal behavior of an actor. And I think this can be very much informed by the join calculus that has lots of thinking going in exactly the right direction, I think. And but the most important is, this is research, and it can't really live just inside of a small room. Then it will not be the best it can be. So it just needs feedback. It needs people using it and saying this doesn't work, or this is great, and this needs to be better. Okay, in the far future, there are a few internal things that currently are more expensive than they need to be in this scheme. For example, every message is put into an envelope just to transport this sender reference, which is one object allocation per message send. We could get rid of that if we switch the stack around. So if we implement untyped actors on top of typed ones, we can actually reap the benefit and get more performance out of the system as well. And then very far in the future, it might even be declared non-experimental. So, this is what I have. Thanks a lot. Are there questions?
This type actors, this only solves at compile time when you know that everything still works. But would there also be some kind of solution to do runtime check, where if you connect two actors together, whether they can actually what one actor produces that the other actor can consume?
So the question was, this is just a compile time check. Can we also make sure that when we introduce two actors at runtime that they actually match? Yes, I thought long and hard about that. I think this registry with the properly typed service keys might solve that. That's what I'd like to try first. And if that is enough, then that's enough. So you just look up with a suitably typed service key and you are guaranteed to get something back that's compatible. Instead of relying on, for example, type tags and manifests that you send around, which might be brittle for serialization or might have other issues. So I'd prefer to keep it only at compile time, if possible. That also means that there will be no overhead, of course. Everything that can be statically ascertained at compile time or is without cost at runtime.
Yeah, so create a new behavior for every message that you so that is an allocation overhead at the moment. Is there any ideas from the future?
So Yeah, so the question is, if we create one new behavior for every message, isn't that also a lot of overhead? Yes, of course it would be. This is why same is magical. If you return same, if you don't need to change behavior, then, well, same just says keep the old one. If you need to change behavior and you need to process 10 million messages per second, there is just no other way. You need to use variables. I haven't shown that on slides. You can, of course, make it a class and not an object, have a variable in there, and the behavior that is in there modifies the variable and reads the variable. That still works. But I would never start out from that, because the other way to do things is safer. And then when you see that performance is not good enough for a certain actor, then transform it. So the question is, how do we still deal with stale actor refs? So there was an actor of a certain type at that address, and now it is no longer. We have a solution for that. It's called Death Watch. So if you're interested in learning when that actor ref becomes invalid, you just watch it, you get the terminated message, and then you know that you will never get a message from it again. So session invalidation. Scala's type system currently cannot express what we would need for that. So it means I have an actor ref, and as long as I have it, I can use it. The thing is, I should be able to express that if you use this actor ref for this purpose, then it's gone. And for that, you would need something like linear types that you can express this. So the method signature says, I have consumed this actor ref. You don't have it afterwards anymore. But Scala, as I said, doesn't have that yet. I'm not sure. I haven't heard Martin talk about that ever. So it will take some lobbying. So if that, yeah?
Would it perhaps be useful to have something similar to Death Watch to know when an actor changes its state and accepts a different kind of messages?
So Death Watch for type of message changes. I would actually just terminate the actor and create a new one and use Death Watch. Build on the thing, keep things simple. That's what I would recommend. So how do we deal with routers? Probably just like they are now, but I haven't figured it out yet. If someone wants to, pull requests are always welcome. No, personally, I just haven't worked on it yet, but I think it should just be modeled similar to what we have. Do we have time for one more?
One question, yeah. Okay. So the question is 2.4 the timeline. So is there any hope that we'll be ready in time for 2.4?
So the question is about the timeline. It is in 2.4. What you've seen will be in there, but it will be very minimal, and it will evolve slowly. This is on purpose, because this is, as I said, research. This is a completely new type of API, so it will probably be at least next year before this will be final. But you will be able, you're already able to play with it just using 2.4 milestone 1. So, thanks a lot.